Okay, welcome everyone. This is the week 6 webinar of the online stats class, and we're halfway through the class, so pretty good. So hopefully, hopefully you're making it through and you're starting to understand the statistics and getting it all out. I am going to share my desktop and talk about what we're doing, and then go through stuff. Okay, so let me talk about the plan today. I'll start out with any questions you might have. And then after that, we're going to get into confidence intervals. So it turns out that from now on, pretty much everything we do is applications. We're done talking about theories or theorems and stuff that you're going to use for later. Now it's using statistics from today through every week for the rest of the entire class. It's how is statistics used? And one of the main uses of statistics is something called confidence intervals. And that's what we're going to get into today is what is the confidence interval? How is it used? How do you interpret it? What are some of the decisions you have to make to come up with a good one, etc. And in particular, today, we're going to have two kinds of confidence intervals. The first kind will be confidence interval for means, and the second will be confidence intervals for proportions. So that's a kind of a big thing in this class, is that it's basically two main kinds of survey questions. One is means, okay? When you get means, and that means you have a quantitative survey question. So that's when you have a survey and you ask a survey question and the person answers with 23 or 5.7, or maybe you do a measurement and you say it's 8 inches. So it's a number. Okay, whereas the other type of the main type will be proportions. And that's when you have the yes/no question, or something that can be turned into a yes/no question. That would be something like, do you plan on getting a master's degree someday? Okay, that's a yes/no question. And you can talk about the proportion of people who said yes. So that's a typical proportion thing. Or something like, did the patient live? That's yes or no. So we'll talk about how do you get a confidence interval for a proportion for statistics. And then after that, we're going to get into something that is also really important. That is, when you are planning on your survey, you want to decide how big a sample do you want so that you have good data. So when we talked about quantitative data, one thing we said, if you don't have over 30, you can't use the normal distribution, and it's mostly worthless. But even if you have a little over 30, you may not have enough data to have a really good estimate. And we'll talk about how many people you need to survey for a good estimate. And that we'll discuss when it's a yes/no question, and we'll also discuss when it is a quantitative question. Those are the two main types. So that is the plan. I want to let you know I'm not done yet, but I've done a bunch of the grading of the projects. There's still a couple more to take a look at. It's not something I can look at in 5 minutes because they're often 10 pages long and there's a lot of them. So maybe by the end of the day, I'll finish. If not, definitely by the end of tomorrow. But probably by the end of the day, I'll finish all the projects. And what I do is you submitted one project for your group. And what I did is I put in the comments directly onto the pages. So if you're the one that submitted it, you'll be able to see that, but your partners won't. So make sure that you share with your partners, however you like to share things, the comments that I made so that they can see it. Does that make sense? And that way, it's not just you. And if you're not the one that submitted it, make sure you ask the one that did to share, so went right up, right and not. Question, can you please remind us what chapters the exam is on and that is due on Sunday? Okay, so the exam, so this is we're in week 6. 6 is an even number. And as you noticed, even numbers is when exams are. So we do have an exam at the end of the week, and the exam technically covers all the chapters we will have done by the end of this week. So that's chapter 1, 2, 3, 4, 5, 6, 7, and 8. Okay, but what I do is the problems that you have to type out the answers instead of just, type a number or click a multiple choice thing. The ones you have to actually type out full explanations, that comes from this week and last week. So that will be chapter 7 and 8. So chapter 7 and 8 will be the last two questions, and they're weighted more than the rest of the questions. So make sure you know how to do that. Best way to study for that is to look at the discussion board from last week and this week and make sure you fully understand how to write stuff out, because you're going to have to write stuff out. So then what I do is half of the exam is from chapters 7 and 8. And the other half is from chapters 1, 2, 3, 4, 5, and 6. So I look at it as half is review and half is new. And that's how all the exams will be like that, is that the week we're on and the week before will be what half the exam is on. And then the other half will be the old stuff. Does that make sense? So hopefully that works. And by the way, it's that's what the halves are. And the exam, is a lot of points. So make sure you practice. They're all randomly generated questions. So you can practice lots of questions. Some you'll have seen almost exactly the same with the numbers changed, because a lot of them come from the homework. Okay, and some come from the discussion type stuff. The last two come from discussion type stuff, and the others come directly from the homework. But remember, everyone's homework is slightly different because they're randomized questions. Okay, any other questions? Good question, though. Any other questions? Okay, I have a question for you, and we're going to have a very small sample size, but we do what we can do. And here is the question. And by the way, I'm not going to put your name on it. So, people aren't going to know who said what. And the rule is you have to answer. You don't have to tell the truth if you don't feel comfortable. But if you're going to not tell the truth, give me something, that is reasonable. So the question is, how old were you when you experienced your first passionate kiss? Okay, so again, if you're not going to tell the truth, don't say, 354. You couldn't have been 354 years old when you got your first kiss. And you couldn't have been 3 years old either, because you don't understand what passionate kisses are when you're that age. So how old were you when you experienced your first passionate kiss? Put it in the chat box. And again, you can direct message if you don't want other people to see, or you can, just put it in. And I want everyone to answer. Okay, so we have our answers, and I'm going to type them in the box. 14, 13, 16, 16. Okay, and again, this is a very small sample size, but it's as big as we're going to get today right now, because that's who we've got here. I know not everyone can make it. There are, by the way, a lot more people in the class than just 4. But this is what we've got. So there's a sample, and we'll do our best. At least it's better than just one. So we'll do our best to use this stuff. Okay, so what we want to do is we want to say I know this is not a random sample. It's not a sample size that's nearly big enough. So we're going to have to make some big assumptions and, live with that. But again, this is more for learning how to do confidence intervals. So when you have numbers like this, remember there are some very important statistics that you can get out of the numbers. One of the statistics is the sample mean. And remember, we use X with a bar on top called X bar to talk about the sample mean. And another statistic is the sample size. Okay, which I didn't put here because that's easy enough. Let me put that too. N is the letter you usually use for sample size. And in this case, I hope you don't need a calculator to know that the sample size is 4. because there were 4 numbers. Okay. X bar, that one you could probably do in your head, but let's work it out. 14, 13, 16, 16. I'm going to copy and paste. Let's go to the calculator. Let's go to one variable statistics. And this is definitely a sample. Calculate, the mean was 14.75. And the standard deviation is, oh, nice number, 1.5. Usually it's not so nice. So 1475 and 1.5. And N is 4. Sample size was 5. If it was 5, then someone put in that I didn't see. 14, 13, 16, 16, 15. Ah, there's the last one I didn't get. That's going to change everything. So now we can put in the 15. Much better. Now I can calculate 14.8. And standard deviation is not as nice a number, but that's okay. 14.8. And then what we've got is 1 point, on scale 1.3, that's good enough. No one really cares about, you know, 100th of a year or 1,000th of a year when you got your first kiss, okay, in terms of, you know, average. So 1.3. And now it's 5 because we got one more person. And SE, so SE, let me put those that in words. Do you know what that's an abbreviation of something that we did last week? You know what that is, SE? You remember? So last week, not too long ago. If I don't see, I'll jump in. That's a standard error. Do you remember that? It's a standard error, which is a standard deviation of the sampling distribution. And if you remember this, to get the standard error, what we do is we use a formula, and that was a fraction, sigma, over the square root of n. Any questions on that? Do you remember that was a standard error formula with the central limit theorem? Okay, and that's approximately equal to, I'm going to put a fraction again, 1.3 over the square root of 5. Why is it approximately equal to and not exactly equal?
Is one of the reasons is that because we rounded the standard deviation?
It has to do with standard deviation, but it's not about rounding, actually. It's a much bigger issue than the rounding. Okay, it has to do with the letter. This is an S, and this is a sigma. Do you see that? So we're using the sample standard deviation as our best estimate for the population standard deviation. Does that make sense? And you're right, we did round. That makes it slightly different, but a much bigger difference is this, especially when you have a sample size of 5, is to say we know the population standard deviation when we really don't. Okay, and that's going to come up later. Okay, and then 1.3 over root 5. We can pop that in. (1.3) divided by the square root of 5. And you get about 0.58. And there's our standard error. Any questions on that? Okay, so this is review of last week, but we need last week's stuff to be able to understand this week. So what we want to do is want to say, well, what we got for the mean was 14.8. Is that the population mean? Yeah, definitely not. Definitely not. Okay, and in fact, our sample size 5, so it's not even that valid. But based on this, do you think the population mean might be 40 years old? What do you think? Do you think it might be 40 years old instead of 14.8?
Probably not.
Yeah, probably not, because our standard error is a little more than half a year. Okay, and that would be like dozens of standard deviations away, which has almost no possibility of happening. Does that make sense? So what we're going to typically do is we're going to say, how far off do we think we might be up to? Does that make some sense? So our best guess from our survey is 14.8, but we know that's not exactly right. So the big question is, if it's not 14.8, could you say between, say, 10 and 19? And would that be a pretty accurate idea? So what we're going to do is we're going to say, not just is it accurate, but we want to say, well, if we want to be 95% confident that our interval is going to actually contain the true population mean, how far out should we go? Any questions on that idea? So what we do is we draw a picture. So here's a standard picture. And the way it works is we're assuming we have a normal distribution. In the real world, you don't have to assume. Why do you not have to assume in the real world you have a normal distribution when you do a good study? No? Came from last week. That's a hint.
Isn't it essentially because of the central limit theorem?
Yeah. In a good study, you're going to have more than 30 in your population, in your sample. And if you have more than 30 in your sample, the central limit theorem says, yes, it is very close to being normal. Do you see that? If you have 5 in a sample, all bets are off, by the way. But that's all we can do with this class right now. Does that make sense? So in the real world, you get over 30 in your sample. You can draw this picture. And then we have our X bar, like our X bar was 14.8. So this number right here would be 14.8. And then you say, we have this normal distribution. We know the mean, we know the standard deviation. So we're going to go out left and right so that the area between the left and right bounds is 0.95 or 95%. And that left and right bound will be called our confidence interval. Any questions on the idea of what a confidence interval does? That way you can be 95% confident, right? That means a 95% probability that the mean is actually in that interval. Okay. And just to note, the reason why you use 95%, my guess is none of you will guess this. It came about, it's like 75 years ago or so. And I don't know if you know, but who controlled everything when it came to, kind of publishing studies and showing everyone? This is history. It was way before all of our times. But if you don't know, it wasn't the internet, by the way, not 75 years ago. New York Times. And the New York Times, actually, they're the ones that decided on the 95%. So the standard because again, in the days of old, not our days, but in days of old, was that if you can be 95% confident, then that's enough for the news to be happy. So we tend to use 95% when you're dealing with news. We tend to use 95% when you're dealing with anything in social science. Social science being like sociology, psychology. Does that make sense? And then they tend to pretty much always use 95%. Okay, that's the standard for that type of study. And that means, what that means is that, imagine, a big news station, whether it be the New York Times or CNN or Fox or, whatever news station you're looking at, they're going to be publishing many, many articles, right? And the idea is they want to make sure that 95% of the articles they publish actually do have the true population mean within them when they do one of these. And they're okay being wrong 5% of the time. Okay, you can't be right 100% of the time when you're doing studies, because then you'd have to get a census, which is pretty impossible when it comes to all of America, for example. Does that make sense? So 95% is the standard for news and social science. Any questions on that idea? So now, based on the empirical rule, if you have a normal curve and you want 95% inside of it, how far out do you go left and right? Remember what the empirical rule said? Again, all of you just turned into your projects. Yeah, 2 standard deviations on either side. Okay. So 2 standard deviations is about what? 1.16 actually. If I multiply 0.58 by 2, 1.16. So if you take 14.8 and subtract 1.16, then you're going to get 13.2. By the way, you're never going to have to do what I just did in your head. If you want to, you can, but you definitely will not be doing things in your head. But you can trust me on the doing in the head. So you're going to get about 13.2. And you can add 1.6. And if you add 1.6, you get 16.4. So our confidence interval will be, again, subtracting 1.6 is 13.2. And adding 1.6 is 15.4. Sorry, 16.4. Any questions on how I came up with that? Okay, and this is all an approximation. We're going to have a little bit better way of doing it later that you're not going to be able to ever do it in your head. You'll have to use the calculator. But what that says is we can say the average age of first kiss with 95% confidence is somewhere between, and this is a population mean age, not the average of these 5, the average of all Americans. Their average age of first passionate kiss is somewhere between 13.2 and 16.4 years old. Any questions on that? Okay, I want to give you a big heads up. Don't trust this data at all because this was a convenient sample of sample size 5, which statistically you should never do. Got it? So I'm just doing this as a class example only. Don't go out and quote this. In fact, yesterday I taught this to my face-to-face class, which is a lot bigger, by the way, because everyone shows up because it's face-to-face. And they had a much higher number, which was 17.1, I believe. Okay, and that's a little more reliable, actually. It was a bigger sample size. It still wasn't over 30, but it was a lot bigger than 5. And I do want to let you know, when I was your age and you looked at college students, any guess on if it was different or the same? This isn't a statistics question, it's a history question.
I think it was lower.
Yeah, it was a lot lower. It was a lot lower. My first kiss, by the way, I was just about 13 years old, so way out of your confidence interval. And everyone laughed at me because I took so long to get my first kiss. Because everyone else was already kissing in those days. I'll tell you, people had, in my age, we had a lot more fun when we were teenagers than you guys did. So I won't say too much about it, but just let you know. 1% laptop, bummer. Okay, this will be recorded, by the way, if your laptop dies. Okay, and if you get home soon, you can re-log on. Okay, so anyhow, that's an example of the use of a confidence interval. Any questions on that? Okay, let me show you something that's a little more reliable, because remember we did this right here, this approximately equal to. We're not going to have to do that. We're going to actually get a much better standard error, and we're going to get a standard error with the fact that we have S and not sigma. And it turns out this was actually developed because of beer. I know that's what you're all thinking, right? There was a guy who he was a statistics professor who also worked in a brewery doing their data analysis. And he realized that when he was doing the data analysis, he'd do a 95% confidence interval, but then they'd look at the population mean later on, and it wasn't right 95% of the time. And he realized the reason had to do with this S versus sigma. And what he did, and this is something I'm not going to get into, but I'm going to just tell you what he did quickly. And that is he did some very intense mathematics. He adjusted the normal distribution with some hard math and created a new distribution that handled the problem of using S instead of sigma. And he named it after his class and called it the student's t-distribution. And we use letter T for it. It looks pretty similar to a normal distribution. It's a little wider out, but otherwise it's got that normal feel. Okay, it's just a little bit wider, kind of a lower peak in the middle. And when you go to my calculator, because I'm a mathematician, so I can handle it. I was able to make sure all the math works, and I created something easy for you. At least I hope it'll be easy for you. And any guess on what calculator number I'm going to use to get this confidence interval that we want? Yeah, number 9. So I did it in order. I tried to make it easy. We have data. And then let's see if that still works. Yeah, I copied and pasted it. I think it was comma 15. Am I right? Yeah. Okay. And now it's going to use the student's t-distribution. And it'll get a better estimate for us. CL is a 0.95. That's what we're using. I just hit calculate. And it's slightly different, 13.18 to 16.42. So it's pretty close. But given the fact that now that we have computers and you can use this, you might as well be more accurate. Even if you're only off by 2 decimal places, you might as well be right. Does that make sense? Because hopefully you agree this wasn't hard. Do you agree? Just put in the data and hit calculate and put confidence level. Okay. By the way, if I use a 90% confidence instead of a 95, let's take a look. If you use a 90%, then that means that if you use if you want to be 90% confident, then in terms of the picture, what's going to happen? Then we're going to have less area, right? We're going to have 0.9 instead of 0.95. So these numbers are going to get squished into the center, and you're going to have a better, kind of a closer estimate. Does that make sense? But it's a give and take. So you get a closer estimate, which feels good because you're like much closer to the true mean, and you don't have to be so wide as your estimate. But if you have a 90%, that means you're only going to be right 90% of the time, and you'll be wrong 10% of the time, instead of being right 95% of the time and being wrong 5% of the time. Similarly, sometimes you'll go to maybe you want a 95% estimate of confidence interval. You really want to be right just about all the time. Does that make sense? Some examples of when you'd want to be right just about all the time is, what if you were doing some medical test and you wanted to look at, let's say this was, you take the medicine and you want to see how much blood pressure varies. Well, if the blood pressure varies a whole lot, that's bad, right? You're going to maybe kill someone. Do you see that? So you really want to understand your medicine. You don't want to be wrong. So in that case, you might want to use a 99% confidence interval, okay, instead of a 95% confidence interval, because you want to be much more confident of being right. Is that clear? Okay. So if we were to have changed this to say 90% and hit calculate, you'll notice the numbers changed. So now it's 13.6 to 16.0. So we have a narrower confidence interval, which is good, right? But you're only right 90% of the time. You have a 90%, you have a 10% chance of being wrong. Okay. Kind of an easier example that I can say is, let's suppose we wanted to find out, let's say the average height of, let's say, female college students. And I said, I am 99.9% confident that the average height of female college students is between 1 feet and 11 feet tall. How much have you learned from my statement? If I said, I'm 99.9% confident that the average female height of college students is between 1 feet and 11 feet tall. Well, what have you just learned from what I just told you?
Not very much. No offense.
Yeah, how stupid I am, right? What a stupid thing to say. Well, of course, the average height is somewhere between 1 foot tall and 11 feet tall for college student women. That's silly. Do you see? So the problem is, yes, you could be very, very, very confident, but at the price of having a very wide spread. On the other hand, what if I said I am 10% confident that the average height of female college students is between 64.1 and 64.2 inches? How much have you learned from what I just said? If I said I'm 10% confident
Again,
that the average height of female college students is between, 64.1 and 64.2 inches tall.
I wouldn't trust someone who says that they're only 10% confident about something. So.
Exactly. You haven't learned anything because there's a 90% chance I'm wrong. Do you see? So it's a give and take. Do you see? More confident, you can have a narrower interval. Less confident, you're going to have less confident, you're going to have a narrow interval. More confident, you're going to have a wider interval. What's the only way to be very confident and have a narrow interval? Let's say I wanted to do the age of first passionate kiss for college students. Because I look at this is pretty wide, isn't it? 13.2 and 16.4. That's a huge variation, right? What's the only thing I could do to have a really good confidence interval with maybe 99% confidence? Any thoughts? There's only one thing I could do. Don't see y'all jumping in.
So the standard error needs to be very small, and in order for it to be very small, well, either the standard deviation has to be extremely small, or your sample size needs to be much larger.
Right. Now, can I change the standard deviation?
No.
No, I don't have that power to make everyone have like the same first passionate kiss year. Good luck. None of us have that power. Do you see that? But I do have the ability with some work to, instead of surveying 5 people, I could go out and maybe ask 400 college students. It'll take me time. You know, I'd have to go and ask a bunch here and then go to some other colleges and ask there and there and there. But a few months later, I might have a good sample of maybe 1,000 college students. And then I'll have a very good confidence interval with a very small margin of error. And the margin of error, by the way, is kind of how far you are away from the mean. So our sample mean was 1.3. Our margin of error, our sample mean was 14.8. Our margin of error was the 1.6. So I could have a small margin of error and have a large level of confidence if I'm able to do a very large sample size. Is that clear to everyone? And that's the only thing. You can't change the standard deviation, by the way. You can only change the standard error, which means you can change the sample size. And the central limit theorem tells us how to do that. So if I want my margin of error to be decreased by a factor of 2, how many people do I need to survey? Any thoughts? Okay, well, I originally surveyed 5 people. If I want to decrease by a factor of 2, I need this denominator to be 2. The square root of what number is 2? Yeah, 4. So I need it to be 4 times larger than what I started with. So if I did a survey with a sample size 20, 5 times 4, then I'll decrease the margin of error by a factor of 2. Do you see how that works? So it is a lot of work to get a smaller margin of error, but it's often worth it, especially when you have such a tiny sample size like this. So you have to decide how much time you have or how much money you have to get the work done. Any questions on this whole idea of confidence intervals? Okay. So let's interpret the confidence interval. I'm going to give you some words on it. And that's with 95% confidence. The population mean age of first passionate kiss. Oops, kiss, not kill. It is between. And now it was 13.2 and 16.4 years old. Okay, I want to highlight something that's really important. And that's population. Okay, we're 100% confident about the sample mean because we asked, we found the mean, and there it was. We know it. But the population mean, we have only a 95% confidence about that it's within this interval. Any questions about how I interpret it? Just to note, see this first word, because I found that if you remember the first word, that helps you like do the whole thing. If you just remember, always start with the word with when you want to interpret the confidence interval, you know, or what is the conclusion. If it's about confidence intervals, then you start with the word with. Got it? Okay, so then what does it mean to be 95% confident? Is that clear? Okay, and I talked about that, but now let's put it in some words, some specific words. And the idea is you can imagine yourself being maybe New York Times or something like that, where you're doing studies over and over and over again. Okay. Every time you do a study, you're going to get a different confidence interval. Okay. But 95% of the time, your confidence interval is going to be a good one, which means it's going to contain the population mean. 5% of the time it won't. So let's put that in words. And that is that if many samples of 5 college students are taken, then each one will produce its own confidence interval. Okay, so if I asked a different 5 people, I'm going to get different answers, and I'll get a different confidence interval. Okay, we can say that 95% of these confidence intervals will contain the true population mean. Age of first kiss. And 5% will not contain it. Any questions on understanding what it means to say you're 95% confident? That's what that 95%, it's a probability. Any questions on that? Just a note, I strongly recommend you actually get a pencil and paper out and take notes on this. I have a template that I wrote. And remember, you can always rewatch the video if you can't write fast enough. And then you can hit pause and do it again. And that's with, I wrote XXX, so whatever percent confidence that you have. It can be concluded the population mean, blah, blah, blah. In this case, it was age of first kiss or first passionate kiss, is between whatever 2 numbers you have. And a template that I have for interpreting the confidence level is if many samples of whatever your sample size are taken, then each would produce its own confidence interval. Whatever percent, so we had 95%, whatever percent of these confidence intervals will contain the true population mean. Okay. And so in this case, mean XXS, that would be age of first kiss. Okay. And whatever percent, like 5% in our case, won't contain the true population mean. That's kind of a template that'll help you get it set up. Because remember, you have an exam you have to take this week, and having that template helps out. Okay. I noticed that when I did the exam with the expected value, and in the webinar, I said you had to have the words many. Do you remember that? Average, likely, and close to. A lot of you did not put those words on the exam question. And it went badly for you. You didn't get the points. Similarly, now I have a template. Okay, and you're allowed to have notes with you. Use it. Got it? But please don't use the words age of first kiss because you're not going to be asked a question about age of first kiss. You'll be asked some other thing. Does that make sense? Okay, so now let's talk about proportions. So we just did an example where the survey question was quantitative. I asked you how old you were when you had your first passionate kiss, and you all gave me a number. You didn't say yes or no. So now let's see what happens instead of quantitative. Let's say, what if you had yes, no? So here's a question I have. I always like to bring in current events if I can. I try and bring fun things like age of first kiss, but I also will bring current event stuff. And so the question is, let's make it a little bigger so you can see it. What percent of Americans see a third Xi? I never had, maybe you can pronounce it better, Xi term, the president of China, as a major problem for the United States. Okay, I don't know if you read the news. I try and bring in new stuff if I can, and this is pretty new news. And that is that it just got announced that the president of China has decided that he's going to take a third term. It's a little different than America, by the way. In China, if he wants a third term, he'd say, I'm taking a third term, pretty much. We can't really do that. But in China, it's different. And the question is this, do Americans see this as a big problem for the United States? How do you decide? Do you think we could ask every American? Yeah, no chance. No chance. You know, there's what, 340 million Americans, I think, or something like that. Some ridiculously big number of Americans. Okay. And yeah, you never, by the time you asked everyone, that'll be hundreds of years from now. You'd never be able to ask anyone. There'd be a new population of Americans. So that's impossible. So instead, you do a survey. And what I did is I relied on a company that did a survey. Not for me, by the way. I just found it on the news. That was Pew Research. They do a nice job in surveys. Kind of my favorite two are Pew and Gallup. I don't know, have you heard of both of those? Yeah, so and there's a lot of others that do it too, but those two they're pretty reliable. They do a nice they usually do a not a convenience sample. They do good sampling, so it's pretty reliable. And their sample sizes are not like what we just did, 5. So let's take a look at what they had to say. So here is the article from Pew Research Center. And it says, few Americans see sorry if I pronounce it right, I could read it, I can't pronounce it, term as a major problem for the US. Other concerns about China have grown, but we're just looking at the third term, as that's a problem or not. Okay. And what it says, if you read the article, I'm not going to read the whole article. Okay. But it does tell us that where was it? First thing is they conducted the study of 5,098 US adults. Okay, very different than our little passionate kiss example, right? This is a study that's much more trustworthy. Okay, could there be some bias? Yes, but the sample size is very good, and they do a pretty good job in doing what they can to prevent bias. It's not perfect, but it's a pretty good job. So it's 5,098. So hopefully, again, one of the big things that I really want you to learn from this class is to be able to read an article and decide whether it's trustworthy or not. Okay, that's a life skill. And that's an important thing, you know, for your whole rest of your life, to be able to say, yeah, I get it. They've done their job and I trust them. Is it perfect? No, but it's pretty darn good. Does that make sense? And 5,098 is a good sample size. So that's N. So let's go over to N. $5,098. Any questions on that? Okay, we need to read a little more. I think that was in the article. Let's say somewhere in here. Where's the third term thing? Remember, read the number. Sorry, but I read the whole article, but I don't remember exactly where it was. Well, maybe we'll just do it. Okay. So President Tsai assuming a third term as the US leader. And we can say that, and the question is it a big problem? And let's go to 41%. So somewhat serious. We'll go with somewhat serious being a problem. Sound good? So 41% say it's somewhat serious. Okay. Okay. So is it exactly 41%? Is that all Americans? No, no. And will we ever know the exact percent of all Americans? Yeah, never, never. We're never going to be able to ask them all. Okay. There are very few times when you're going to know all. Let me tell you one of them. And here's the hint. We're going to know on November 9th. And what is that? Not this, but something else.
Midterms, right?
Yep, yep. And then we'll know exactly. We'll know of all the people who voted. We'll know what percent voted, say, for Governor Newsom, for example. And we'll actually know that percent. We will have a full census of all voters because they do look at every voter. Does that make sense? Okay. Sometimes it takes another day or two to get the last mail-in ones in, but might be November 12th. But the point is we'll know, right away. Does that make sense? Okay. Yeah, maybe I should say, because of my personal experience, the next day you don't always know. Do you know why my personal experience says that? Because when I ran for election, the news said I lost the day after, but I won. So when there was an election, I actually won the election, but they didn't know for 2 more weeks. So just note that. I don't know if I told you about that, but that happened. So it was one of those weird things.
But you ran for something?
Yeah, I ran for school board and I won by 3 votes. But they didn't know until 2 weeks because they had to get all the mail-in ballots.
And that was like the mail-in ballot sort of thing was still kind of a recent and ongoing controversy, right?
It's always a controversy. Yeah. This was 15 years ago, so or something like that. 15, 16 years ago, something like that. Yeah, maybe 14. But anyway, so it might not be the exact day after. But anyway, let's go through this. 41%. Now, what letter is 41% in our statistics language? Here's a hint. I need to do an equation because I can't just type it in. No? That's p hat. And let's make a hat on it. I think it's one of these. There it is. There we go. So p hat is 0.41. Any questions on that? So p hat is 4.41. By the way, our number of yeses. How do I get the number of yes answers? Yeah, I take my p hat and I multiply by 5,098. I don't want to do that in my head. My guess is you don't either. So I'm going to go 0.41 times 5098, I think it was, right? Yep. 98. And we should round because these are people. Can't have 0.18 people. So 2090. Okay. By the way, was our sample size large enough to use a normal distribution according to the central limit theorem? Okay, how do you tell? So if I do, instead of 0.41, if I do 0.59, because that's the percent of no answers, that gives me 3008. All right. I made you promise something last week. What number did I say you should never use when it's a yes/no question? Yeah, never use 30. When we have a yes/no question, what are we comparing it with? Or them in this case, what are we comparing them with? Do you remember?
Wait, is it really a yes no question? Because I thought there were like four. There's like serious and somewhat serious and
Right, right. So what we're looking at is we're looking at the proportion of people who said it was somewhat serious. We're
Okay.
getting a confidence interval for this 0.41. Does that make sense?
Yes. Yes.
Yeah.
Makes sense.
So it's definitely yes, no. Did you think it was somewhat serious? And it's not 30. What's the important number when it's a yes, no question? I'll see you 5. Yeah, 5. Okay. 2090 is definitely bigger than 5. 3008 is definitely bigger than 5. So that tells us that yes, we can use a normal distribution. Everything is good. Otherwise, you give up, by the way. Okay, if you don't have the bigger than 5, you give up and say we need to survey more people. You don't even try to do a confidence interval. Got it? With proportions. You can't even make an assumption. There's no assumption to make. You just give up. Okay, and ask more people. All right, so now what I'm going to do is I'm going to show you on the calculator. And what calculator do you think I'm going to be using? Which one do you think I'm going to use now? Not a trick question. It's not supposed to be too hard.
Wait, so I was initially going to say 9, but what is like the 10th calculator using data? What is that?
Okay, so it's not 9 and it's not 10 because those are for means. We're not looking at means. We have a yes, no question. Do you see that? So which number is it? It's not 7. That's just to find a probability. We want a confidence interval. That's a hint.
So it would be 12 because we're dealing with
Yeah.
proportion.
Exactly. It's 12. Proportions are for yes, no questions. So confidence interval for proportion is what we want. Any questions on that? Does that make sense? Okay, and it's very important that you know how to find the right calculator number. Okay, because you'll be given a paragraph, but if you go to the wrong calculator, you'll like, now what do I do? Do you see? So it's really important you go to the right one. If you go to the right one, it's really easy. So our N was 5,098. Our X is a number of yeses, by the way, which was 2,090. Confidence level, what do you think a good confidence level is for this? Yeah, probably 95% because this is political science. Political scientists always use 95%. So 0.95. By the way, I'll tell you an example where I use 90%. I did some consulting work, statistical consulting work for the Forest Service. And they asked me to use 90%. And hopefully you know the big saying, the boss is always right. I let them know what it meant to use 90%. Just wanted to make sure they knew. And they said, yeah, we know, but you have to use 90%, not 95%, because we don't have enough funding to have a large enough sample size. We want to make sure that we have a smaller margin of error. So I said, okay, boss is right. So sometimes you have to use something else, if the boss tells you or whatever. That was my personal example of one. So again, it does happen. Hit calculate. And there we have it. So maybe I'll round to how about a percent plus 1 decimal place? So 39.6% to 42.3%. I just turned it to percents because it's a little easier to understand with percents, because that's how they put it in there. And what we could say is that with 95% confidence between 39.6% and 42.3% of all Americans are somewhat concerned about Psi getting a third term. Let's make that bigger so you can see it better. I want to highlight this word right here, all. Again, you have to be referring to the entire population, not the sample, and you have to be very specific about it. I will take out points if you don't. Is that clear? Any questions on this conclusion here? Okay. And I think I'll say what it means to be 95% confident, not type it out just to save some time. But what we can say is that if many samples, if many samples of 5,098 Americans were surveyed, then each one would produce its own confidence interval for the percent of all Americans somewhat concerned about Psi getting a third term. 95% of these confidence intervals will contain the true population proportion, not mean, proportion of all Americans that are concerned about Psi getting a third term. So very similar to the mean, except now it's about proportions. Any questions at all about this example? Okay, so I just want to let you know, I only have time to do like one example of each type. So I do strongly recommend, reading the book, watching the other video, looking at my example on the discussion post. There's lots of examples. So, you get a couple in this lecture, but then you'll get more as you read through and do other stuff. All right, so now comes the next question, and that is sample size for the mean. Okay, I'm going to throw a little bit of math at you. So hopefully you remember the central limit theorem says that the standard error, sigma sub x bar, is equal to the population standard deviation divided by the square root of the sample size. That was last week. And that was a key formula. All right. The margin of error is the Z. Remember we used 2 when we had 95%? Because 2 standard deviations gave you about 95%. Do you remember that? So the Z in that case was 2. Okay. And by the way, if you want to be more accurate, it's 1.96. That would be 2 decimal places, but 2 is good enough. If you wanted a 90%, then it would be 1.645. Again, I just happened to, for some silly reason, remember these numbers. You don't have to memorize them. But if you take that number and you multiply by the standard error, that gives you how far from the mean you're going to have to go to get to the boundary. And that's called the margin of error. Okay, the formula for that is Z sigma over root n. And then if and I'll just do this really fast, multiply left and right by root n, divide by E, and take a square of both sides. And you get n equals Z sigma over E quantity squared. So algebra. Any questions on this formula right here? Okay, so now I can do an example. Let's suppose you wanted to find a 95% confidence interval for the population mean hourly wage of nurses in California. Okay, might be interesting. And, if you were interested in becoming a nurse, then you might care about what your salary is going to be, right? Okay, Based on a preliminary study, the standard deviation is assumed to be $25 an hour. I will let you know I made up that number. I didn't really do a preliminary study, but you can imagine doing a preliminary study. Okay. If you want a margin of error of no more than 50 cents, because the idea is if you're off by 50 cents, that's probably not going to change your idea of whether you want to take a job or not. What do you think? You don't really care about 50 cents. So that's, even if 50 cents an hour, which adds up a bit. So I'm going to go 50 cents, but if you do, you can go 1 penny if you want. But we're going for 50 cents. So then the question is, how many nurses must you survey? Because we're surveying nurses to find out how much money they make. Do you see? Any questions on that? Okay, so there's a couple ways of doing it. One way, I'm going to do it this way just to show you, is we have this wonderful formula right here. I'm going to copy and paste it over here. As I mentioned, with 95%, it's 2 or 1.96 is to 2 decimal places times sigma. Sigma is 25. That's the standard deviation. Divided by E. E stands for margin of error or error. And we want our margin of error to be no more than 50 cents or 0.5. Any questions on that? Have I lost you on any of the math here? All right, so then of course, you probably wouldn't want to do this by hand, am I right? So if you want, you can use a calculator. And again, 1.96 times 0.25.
I think it's just 25, not 0.25.
Oh, you're right, $25. Divided by 0.5. Outside I want, there we go. And then square. So you would need to survey 9,604 nurses. So this would be a big survey, right? If you wanted a 95% confidence interval with a margin of error of no more than 50 cents. Any questions on this example? Okay, I wanted to show you this because this comes right from the central limit theorem. But I did something that actually made a few other statistics instructors upset, is I made it easier. Because some people want to make sure you know the central limit theorem formula and actually do this. But let me just show you another way. If I go back to the calculator menu, any guess on what calculator I might want to do? Looking for a number. Number 9, not quite. Number 13, good idea, but we don't have a proportion. This is right? The survey question is how much money did you make or do you make? And that's not a yes, no question. So what number? Tell you what, 9 and 13, you're both wrong, but if you take your average of your 2 guesses, 12 isn't the average of 9 and 13. Yeah, 11. Sample size. And it's for a mean, not for a proportion. Do you see? So I can click on sample size for a mean. It asks for a sigma, which was 25. It asked for E, which was 0.5. And it asked for the confidence level. And we wanted 95%. So 0.95. and it's 9,604. So what we need to do is survey 9,604 nurses. Any questions on using the calculator? Any questions? By the way, in the real world, what you would do is you would plan on surveying 10,000, because if any of you have ever been a manager, there's always a few things that go wrong, and that way you're a little higher than you have to be, and then if something goes wrong, you're still okay. But that's not math, that's management. Stuff always goes wrong. So you usually round up a bit. But mathematically it's 9,604. Any questions at all on this example? Okay, so the nice thing is it's not that hard. Do you agree? To find the sample size needed. So in the real world, what do you think the hardest part of, say, a study like this would be? Right? There's a lot of things. One is coming up with like what you're interested in. The other is coming up with your sample size. The other is conducting your study. The other is analyzing your numbers and deciding and finding out what the confidence interval was. And then the final one is interpreting. What do you think the hardest part is in terms of the process? And by the way, one is much harder than all the rest combined. Thoughts?
I'm thinking getting a study that's actually trustworthy and one you could conduct the test on is probably the most difficult part.
Deciding what to do to make it trustworthy actually isn't that hard. Should I tell you the hardest part? Actually doing the survey and asking them. Do you know how long it would take to find 9,604 nurses and ask them the survey question and get them to answer? Right, that's going to take days and days. All the other stuff might take an hour each. Do you see the difference? So what you want to do is you want to make sure that all of the other stuff you've done is managed really well. You want to spend, the extra hour to get that right, because in the real world, it's going to take a whole lot of effort to actually conduct the survey. In terms of time, it's all about the conducting. That takes all the time. Okay, in this class, you're not going to see that because you're not going to have to ask 9,604 of anything. Do you see that? But in the real world, that's just the way things go. Is the hardest part is always the survey itself. It takes a lot of work. Does that make sense? Yeah, just the door-to-door stuff, right? Or in this case, it'd be hospital to hospital. Just take forever. So that's just a note, is that you want to plan right, because that taking extra time planning is so minor compared to the survey itself. Okay, so now let's do another example. And let's talk about a yes/no question. As I mentioned, a lot of the class now from last week on basically breaks it up into the quantitative question, the number answers, to the yes/no question. So you're going to see that over and over and over again. We just did the sample size for the quantitative study. Now we're going to do a sample size for a proportion or a yes/no question. Okay, so again, in this case, I'm not going to go through the math, if that's okay. I'll show you with the calculator. I could do that, but it's a lot of algebra. Instead, let's do an example. Okay, let's suppose you want to find a 99% confidence interval for the population proportion of cars in the United States that are EVs, electric vehicles. Okay. If you want a margin of error of no more than 3%, how many cars must you look at? Do you understand the question? Okay, so let's go ahead and take a look at that. Well, first thing, our confidence level, right? CL equals 0.99. 99%. We want a margin of error. I use the letter E for a margin of error. Is equal to 0.03. Don't forget, when you turn a percent into a decimal, you got to move the decimal over 2 places. So that's why it's a 0.3, not a 3. Okay, so there's our confidence level. There's a margin of error. Any questions so far? Okay, and then the next part will be the hard part for the first example, possibly, and then all the rest of the time, hopefully it'll be easy. So let's go back to the calculator menu. I'm saying hard because you guys had trouble with this in the last today. What number calculator do you think I'm going to be using now? Good, you got it right this time. 13, sample size for proportion, because this is a yes/no survey question, right? Was that car an electric vehicle? Yes or no? And we want to find out how many cars you need to look at, which is sample size. So sample size for proportion. And there are actually, here there's two choices. No estimate for P, have an estimate for P. Do we have an estimate for the population proportion for part A on this example? Based on what's given, do we have any idea what the population proportion is for electric vehicles? Yeah, no, there's no information given. So in this case, when you don't have any estimate, then you get no estimate for P. Make sure that's checked. Then our E was 0.03. And CL, our confidence level, was 0.99. And I hit calculate. It's 1,844. So the answer is, you must look at 1,844 cars. Any questions on this part A of the example? I want to give you a note of something that we've looked at before, and that is when you did project 1. What did I tell you? How many people did you have to survey? At least how many? Yeah, more than 30. So minimum was 31. Okay, and I told you you had to do a quantitative study. Okay, and by the way, project 2 is going to have those same rules. There's going to be one little extra piece, which we'll talk about next week, but it's going to have similar rules. And the reason why I'm having you do a quantitative study, it turns out that if you're ever going to do a yes/no survey question, and you want anything with any kind of just general accuracy at all, you're going to be in the realm of over 1,000 to ask. And I don't feel comfortable making you do a survey of over 1,000. I think then I would be an evil person, and I try not to be. You may think I am sometimes, but I try not to, make it really evil. But asking 31 people or taking a data set of 31, I don't think that's too bad. So it turns out when you have the yes/no question, you tend to need a much higher sample size than if you're going to be doing a quantitative study for most examples. Okay, now let's look at part B. If you look at last year's data, 2.2% of all cars are EV. Okay, I found this using Google. I went online. That's what it said. So how many cars would you need to look at for the 99% confidence interval? What's different for part B that we didn't have for part A? Yeah, now we have an estimate for the population proportion, whereas in part A, we didn't have an estimate. And note 2.2% as a decimal, what number is that? So how do you convert this to a decimal? I want to make sure y'all know how to do that. 2.2%. I don't make you do too much math in this class, but this is one of them that you definitely need to know. Yeah, 0.022. Okay, don't go 0.22. It's 0.022 because it's 2 places over. So 0.022. So I'm going to go back because now we have an estimate. If I click have an estimate, now it actually puts in the box estimate for P. And that's 0.022. And everything else was the same. And I calculate N. And everything changed. All of a sudden, it's 159. It's a huge difference. So now we need to only look at 159 cars. 159 cars. Huge difference in terms of the amount of work it takes. So having that estimate is often very worthwhile. And a lot of times what you would do, even if we didn't know last year, what you might do is maybe survey 50 cars and look at the percent of those 50 cars and then use that as your estimate and then continue. So often it makes a big difference. It turns out, and it has to do with the math, which I'm not going to do all the fancy stuff, but it turns out that if you're very far from 50% in terms of your estimate, then the number that you have to survey is reduced by a lot. If you're close to 50%, then the number that you have to survey is not reduced much at all. And if you're exactly 50%, it turns out then it doesn't change anything. Any questions on this idea? It's very important when you're going to do a study, okay, that you know how to make your plan. And this is the planning part, because you don't want to do too few. Because if you do too few, you're going to have a really big margin of error and useless data. You don't want to do too many. So if you do too many, it's going to be very expensive, because in the real world, you got to pay to get this study done. Does that make sense? And then you're going to be wasting a lot of money. So for the real world, you really need to get this done and get it right so that you don't waste money and you end up with results that are reliable. All right, so the last thing to do is a secret word. And the secret word for today is the word with. And that's because if you remember, when we are explaining what the confidence interval is, you start out with is your first word, like with 95% confidence, blah, 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 or with 99% confidence. So with is a secret word for it. I try to make an important word that you wouldn't guess. Maybe you all would have all guessed with, but I doubt it. So that's your secret word for this particular webinar. And just want to let you know, again, this is the week of confidence intervals. We'll do a little more with confidence intervals. It will be part of your project 2. Now that project 1 is over, although I haven't graded all of them, but most of them. Now that project 1 is over, pretty soon we'll be starting to think about project 2. It's a little too early now because we don't have all the concepts down. Next week, we'll have more of them. And confidence intervals are a big part of project 2, but you're going to be doing what's called a comparison study. So it won't be like project 1 where you just looked at one survey question. With project 2, you're either going to look at 2 survey questions, it turns out, and compare the answers, or you're going to be looking at 2 groups and compare the groups, like men versus women or something like that, or, you know, Californians versus Nevadans or something like that. Or maybe it's going to be 2 different things, like, I don't know, how old were you when you got your first job and how old were you when you got your first car? Right, those would be things that you might compare. So you're going to do a confidence interval for that. So I want to mention that, you know, it's a little early to think about project 2, but I want to give you little hints on project 2 right now. Okay, so that's pretty much all I have to say. And as always, I'm going to stop the recording and also stop the share.